Looks like it is here. Damn, son. What's going on? You just froze? At least one of the numbers is too big. We can't show the solution. Damn. It's not possible? What's going on? Oh, it already has the times. 627 times. Wait, hold on, bro. Damn. Go. So it pretty much does it. Doesn't give me the full. Doesn't give me the full answer. I think I might just do it just this way. It's kind of weird. I got a different answer. 3.
Whereas B times D is 26.
Hold on, I'm gonna try a few more. Same thing we get over here. That's probably how I'm gonna return it. I'll still break it down like that method that he's showing, but I might just return it this way because it doesn't look like it's possible. Damn. Sheesh. Okay, so that didn't work. This one over here, let's see.
Next, I'm going to do something even still more inscrutable. I'm going to take the sum of A and B. I'm going to take the sum of C and D. And then I'm going to compute the product of those two sums. That boils down to computing the product of 134 and 46, namely $6,164. Now, I'm going to subtract our first two products from the results of this computation. That is, I'm going to take 6,164, subtract 2,652, and subtract 672. You should check that if you subtract the results of the first two steps from the result of the third step, you get 2,840. Now,
compute third step. Product 2, we'll name this one product 1. Product 2 is going to be product 1 minus, what is it? Product 2? Oh, I didn't even know there was, damn, I completely missed that. Wait, hold on. It's A times C. I want to have them in order. A times C, product 2 is B times D. We'll name them like that. We'll do steps. Step 1, step 2. We'll do step 1. 622, step 2. Alright, let's step 3. That's what I had earlier. So I'll do this one. We'll do A, B, C plus D, which is what I had earlier as well. It's 61. Oh. And now step 4, step 4 is step 3 minus step 2 minus step 1. What do we get? $28.40.
Now, I claim that I can take the results of steps 1, 2, and 4 and combine them in a super simple way to produce the product of x and y. Here's how I do it. I start with the first product, AC, and I pad it with 4 zeros. I take the result of the second step and I don't pad it with any zeros at all. And I take the result of the fourth step and I pad it with 2 zeros. If we add up these three quantities from right to left, we get 2, 5, 6, 6.
So you pad it with 4 zeros. Step 5. Alright, so step 5 we're gonna have product, what is that? Step 1, we're padding it with 4 zeros, so I'm gonna multiply it times 10,000. And then I'm gonna add that times step 2. And then I'm gonna add this one, step 4, padded with 2 zeros. Step 4, padded with 2 zeros, so multiply that by 100. Step 5 should be 7, I think it was like 700,000. Or 7 million.
6007. If you go back to the previous lecture, you'll note that this is exactly the same output as the grade school algorithm. That is, this is in fact the product of 1, 2, 3, 4, and 5, 6, 7, 8. So let me reiterate that you should not have any intuition for the computations I just did. You should not understand what just went down on this slide. Rather, I hope you feel some mixture of bafflement and intrigue. But more to the point, I hope you appreciate that the third grade algorithm is not the only game in town. There's fundamentally different algorithms for multiplying integers than what you learned as a kid. Once you realize that, once you realize how rich the space of algorithms is, you have to wonder, can we do better than that third grade algorithm? In fact, does this algorithm already do better than the third grade algorithm? Before I explain full-blown Karatsuba multiplication, let me begin by explaining a simpler, more straightforward recursive approach to integer multiplication. Now, I am assuming you have a bit of programming background, in particular that you know what recursive algorithms are. That is, algorithms which invoke themselves as a subroutine with a smaller input. So how might you approach the integer multiplication problem recursively? Well, the input are 2 digits, each 2 numbers, each has n digits. So to call the algorithm recursively, we need to form inputs that have smaller size.
So you get x by dividing 2, a plus b. Let's see. So let x2 actually a plus b, c plus d. What does that do? x2 equals 10 What's the number? X equals A plus B. Where A and B are n divided by 2 minus digit n.
Less digits. Well, we already were doing that in the computations on the previous slide. For example, the number 5, 6, 7, 8, we treated the first half of the digits 56 as a number in its own right, and similarly 70.
Digit numbers. Digit numbers. So there was 4. So it was 4 divided by 2. $56 plus B. Is that what it is?